Okay, so on the last page of the packet, I'll flip back real quick. We had this weird looking graph that had um, a derivative that didn't exist at a point, and that's going to lead us into talking about differentiability. So a function is said to be differentiable at x equals c if the derivative exists at that point. Um, so there could be times where the derivative doesn't exist. And there's going to be four cases in particular where the derivative doesn't exist. And the first one we'll take a look at here is when the graph has what we call a corner point. So if I think about this as the absolute value of x minus 2, all right, so absolute value of x minus 2 is a piecewise linear function, right? We've got a line with a negative slope, and in particular, it's actually a slope of -1. So I could actually graph this. I'm going to graph the derivative function up here. It's actually a pretty simple one. For all the values on this side, the graph is going to have a slope of -1. So f prime is going to equal -1 constantly. Then boom, right at 2, it just changes, instantaneously changes, which means that the derivative graph, so this is number 1's f prime graph, the slope automatically just jumps, right? We have a jump discontinuity in f prime. And the derivative itself, you can see I've got 2 open dots because I can't draw a tangent line at that point. And so f prime doesn't exist there. It's not differentiable at x equals 2. The second example here, we have 1 over x minus 2 squared, a function that just doesn't have is not defined at x equals 2. That graph, the derivative of that should not exist. It shouldn't automatically all of a sudden start to exist at x equals 2. So at x equals 2, I mean, you can see that the slope is pretty flat, and then it starts to gradually get steeper. Right around 1, maybe it's getting really steep. And so this is what f prime would look like for number 2. And so over there, all of a sudden the slope is really steep. Now, this is what trips people up here, is that over here on this side, it starts decreasing. So f prime is going to be negative. And so it's really steeply negative at first. So f prime is going to be really negative and gradually flatten out, right? Gradually approaches 0 because the slopes are flattening out over here. So this is f prime for number 2, and you can see that it doesn't exist at x equals 2. Vertical tangent. All right, so now we have a graph that has a discontinuity, or sorry, the derivative for number 3 is going to have a discontinuity at x equals 1. All right, so let's kind of think about this, what's happening here. Right, slopes are positive, getting a little bit more positive, and then right here at this point, right, it's a cube root function that's been shifted. The function's continuous, but the slope is not defined, right? What's the slope of a vertical line? Infinite. So this derivative graph is going to be kind of flat, right? Close to 0. And then as it gets closer and closer to x equals 1, it goes off to infinity. Now, the thing is, what makes this different from number 2 is that now the graph's slopes are still positive, right? Still increasing, but now it's slowing down how much it's increasing. So this f prime graph will be very positive and gradually slowing down how positive it is. And this is an abstract concept that a lot of students struggle with. So this is the graph of f prime for number 3. And then number 4, the graph has what we call a cusp. And so that's actually similar to the picture we saw on the previous page. The graph is decreasing And it's decreasing kind of slowly at first, maybe slope of -1, then negative like 1.2, -2, -4, and it's almost approaching vertical again, very similar to the way this is, but instead of being what looks like a smooth differentiable curve, although it's not, um, is it, boom, it starts jumping to increasing and increasing to infinity. And this graph actually is going to look very similar to the derivative graph for number 2. So f prime, we're going to have a vertical asymptote essentially at x equals 1, right? It's a negative, right? The slope looks kind of negative here. And it's getting more and more negative until it's approaching x equals 1. It's getting very negative, approaching practically negative infinity. Then right at the other side of 1, all of a sudden, boom, it's a positive slope. And it's slowing down how much it's positive, but it's still positive. So there's our graph, the derivative for number 4. We can actually verify differentiability, and it's going to be easiest to do it using this formula, using the alternative form of the definition of the derivative. So this is something that you are expected to have memorized, this formula. Okay, so let's take a look at a couple examples. So example A, we have an absolute value of 2x minus 6. It is an absolute value function, so we're expecting a corner or a jump discontinuity. So again, the limit definition is the limit. So the alternate form is limit as x goes to c, which in this case is going to be 3, of, I'll write it still in function notation first, so f of x minus f of 3 over x minus 3. And for that, now when I do plug in for the function values, the limit as x goes to 3 of absolute value of 2x minus 6, right? That's just f of x minus f of 3. Well, if I plug in 3 here, I get 0, right? Absolute value of 0. I don't even have to really put that there. Over x minus 3. So that part's gone. Okay, so I'm going to slide up here. So we get the limit as x goes to 3 of, well, this is a GCF of 2, right? So I can pull the 2 out because it's a positive number. I can pull it outside of the absolute value. So I get 2 times the absolute value of x minus 3 over x minus 3. Now, this one is just kind of analytical based on what we have memorized about this graph. Piecewise, we're going to end up with positive 1. So the limit from the left, and it could be the limit as x goes to 3 from the left. And that would come out to be, I'm going to write it out as the function I have. That comes out to be -2. Right? Because if I think about numbers, if I plug in numbers smaller than 3, I get a positive up top, but a negative on bottom. And so that's why that's going to come out to be -2. But if I do the limit as x goes to 3 from the right, I'm going to end up getting +2. And so right there, because the limit doesn't exist, the function or the derivative won't exist, right? The limit doesn't exist, the two-sided limit, right? So f prime of 3 does not exist because these two things are not equal. All right, so let's try another one of these. All right, so I'm going to go ahead and skip this step of writing it as the f of x notation and just jump right down to this, right? So we're looking at the limit now. It's a c value 2, so it's the limit as x goes to 2 of f of x. Well, this is f of x. And if I plug in 2 there, we get 0 to the 2/3, so it's just 0 over x minus 2. And I could actually just do properties of exponents here. Limit as x goes to 2 of x minus 2 to the 2/3 over x minus 2. And I end up getting, by property of exponents, right, because this is really to the first, there are more x's on bottom, so I could really rewrite this as the limit as x goes to 2 of 1 over x minus 2 1/3, right? 2/3 minus 1 is 1/3, and then 1/3 is going to be on the bottom as the exponent. And now, by direct substitution, we get 1 over 0, which means that, again, this does not exist. Therefore, f prime of 2 does not exist. All right, and so that one's going to be a cusp, right? This was a corner. This one's going to be a cusp. And that's because this is a jump discontinuity. F prime has a jump, right? F prime, jump in F prime, and then this one is an infinite discontinuity. So that's actually going to be a cusp. Function does exist. It's continuous, but the derivative does not. Okay, so last one here is essentially is a piecewise function. And so we are just going to check to see first if this just has a discontinuity in itself. So first we want to see does the limit as x goes to 2, 1 on the left, f of x. And we want to make sure first that this is true. And question whether that's true. If I do the limit as x goes to 1 from the left, I'm plugging in 1 into this piece of the function. And I get 1 squared plus 2 is 3. And if I plug in 1, so it is continuous. So far we have continuity confirmed. So now we just need to check whether the derivative exists. So the way we're going to do that is by using, again, the alternate form. Right, so we're going to have to do this one as 2 separate statements. The limit as x goes to 1 from the left of f of x minus f of 1 over x minus 1. And the limit as x goes to 1 from the right of f of x minus f of 1 over x minus 1. And so when I'm doing the limit as x goes to 1, f of 1, right, and it's important to recognize that f of 1 is 3, right, because I'm plugging in to that. Okay, but when I'm doing the two-sided limit here, when I do the limit as x goes to 1 from the left, we're getting, let's see, it's the limit as x goes to 1 left of x squared plus 2 minus 3, so it's x squared minus 1, right? And maybe I'll show the work for that. I said it out loud, but x squared plus 2 minus 3 over x minus 1. And we're comparing that to the limit from the right, which would be 3x minus 3 over x minus 1. So then this becomes x squared minus 1 up top, right? That's just combining like terms. I could just rewrite the top like that. And then this becomes 3 parentheses x minus 1. And that's just GCF factoring. So what I'm hoping is obvious based on the limits unit we did. The x minus 1s will cancel, and so this is the same as the limit as x goes to 1 from the left of x plus 1. And this is the limit as x goes to 1 from the right of just 3. And my answer for this is 3. My answer for this, when I do direct substitution, is 2. 2 does not equal 3. Right, so the two-sided limit does not exist, and therefore this is f prime of 1 does not exist. All right. Okay, that went a little long. I apologize, but hopefully that should explain a few things.